All right, we have a satellite going around the Earth. It's in space, near Earth orbit is what they call this. The satellite is the red dot. Here's the center of the Earth. This is the surface of the Earth. Now, we're going to assume that the satellite is going around in uniform circular motion. The truth is that anything in orbit really goes around in an ellipse, but let's just make it easier. It's going around in a circle. G is the gravitational constant, 6.67 times 10 to the negative 11. It's a lot of information here. The mass of the satellite, 3,200 kilograms. The height of the satellite above the surface of the Earth, the red arrow. The height of the satellite above the surface of the Earth, which we call the altitude, is 2,200 kilometers. Be careful because that has to be in meters. So 2,200 kilometers is 2,200,000 meters. Will I really put that in kilometers on a test? Oh, yeah, probably. You have to remember to convert it. The mass of the Earth is a given quantity. You will be given that number, 5.98 times 10 to the 24 kilograms. And the distance from the center of the Earth to the surface is another given quantity, 6.38 times 10 to the 6 meters. Now, the satellite circle, this is circular motion, so you need the value of r. Well, the value of r is not measured from the surface. This is one of the most common mistakes. It's not measured from the surface to the satellite. It's measured from the satellite center, which is right here at the center of the Earth, out to the satellite. So be sure to add these two numbers to get the overall value of r. That's the radius of the satellite's circle. I've already done that for you here. R equals the sum of the two, h plus the radius of the Earth. H is 2,200 kilometers, which is 2.2 times 10 to the 6. That's 2.2 million meters, plus 6.38 times 10 to the 6 meters. So you have to add meters and meters. And this comes out to be 8.58 times 10 to the 6 meters. And that's the value you use for R. All right. I need to figure out the gravitational field strength. The gravitational field strength. Gravitational field strength of the Earth at that point in space. That's the same thing as the acceleration due to gravity. The gravitational field strength of the Earth, which in my classroom is 9.8 meters per second squared, what's that value? 2,200 kilometers above the surface of the Earth, above my classroom. So we're looking for little g. We will have done this proof in class to come up with the equation for little g. It just comes from putting mg, how we calculate weight, next to Newton's law of gravity, big G, m1, m2 over r squared. And you get this for the Earth, it's big G times the mass of the Earth, all divided by r squared. R being the distance from the center of the Earth out to that point. Again, this is the gravitational field strength of the Earth. The satellite has nothing to do with it. You know that's true because Galileo found out that all things fall independent of that thing's mass. It has only to do with the Earth. All right, what is this? 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24, 124, divided by 8.58 times 10 to the 6 squared. Don't forget to square it. Don't forget to square it. That's a common mistake. And it comes out, I mean, that's an awful looking calculation. If that had been in my classroom, it would have come out to 9.8 if we'd used just RE right here. Just that, I would get 9.8. But I'm not. We're not there. We've got a bigger radius. This comes out to be 5.42 meters per second squared. What does that mean? It means if we were to stop this satellite right here, just let it fall towards the center of the Earth, it would accelerate at 5.42 meters per second every second towards the center of the Earth. Of course, it's going to increase as it gets closer. That's what that means. For part B, let's look for the force of gravity, all right? The gravitational force of attraction between the Earth and the satellite. What's the gravitational force of attraction between the Earth and the satellite? How much does it weigh up there? But we don't really talk about that. We talk about this gravitational force of attraction in a scenario like this. Well, you could use Newton's law of gravity, big G times the mass of the satellite times the mass of the Earth divided by r squared. You can, it'll work, but what a pain. You've already done the big G times the mass of the Earth all over r squared. Why not just multiply that times the one missing thing, which is the mass of the satellite? Again, FG is big G times the mass of the satellite times the mass of the Earth over r squared. You've already done a lot of the work. That's 3,200 times 5.42, and it comes out to be 17,300 newtons. Part C, what's the speed of the satellite? Well, if the centripetal force is centripetal force on a satellite is due to gravity, so that is the centripetal force, then it should follow that the centripetal acceleration is due to the acceleration due to gravity. In case you don't believe me, centripetal force is due to gravity. Well, what's gravity? It's m times g. That's the mass of the satellite times g, which is 5.42. So it's that number, 17,300. That's the centripetal force. Well, that causes the satellite to go in a circle, all right, v squared over r, all right, mv squared over r, centripetal force, mv squared over r. Mass of the satellite, the thing going in the circle, and the mass of the satellite cancels. And so g equals v squared over r, or v equals the square root of g times r, which is 5.42 times that r. And that comes out to be, what is it, 6,819 meters per second. That's a lot. Just FYI, that's over 15,000 miles per hour. And then the last question you'll be asked for is the orbital period. All right? Orbital period. In other words, how long does it take to go around the Earth once? Well, you know that for something going around in a circle, at constant speed, it's distance over time, which is circumference over period for a circle. So that's 2 pi r all over t. Solve for t. So t equals, I'm sorry I'm getting in the way here, 2 pi times that r, which is this huge number, 8.58 times 10 to the 6. All over the speed you just calculated, 6,819. And you get 7,906 seconds. 7,906 seconds, which just, oh, by the way, is just over 2 hours. It takes just over 2 hours to go around the Earth once, and it's 2,200 kilometers up. Just over 2 hours to go around once. It's pretty fast.